Good morning to all participants. Welcome to a two-day presentation on the remarkable intersection of microwave and biomedical applications. So in this presentation, I will delve into the breakthrough achieved so far and explore the exciting future prospect of microwave technology and biomedical applications. My name is NOOR ASAN. I'm from Microwave Research Group, Center for Telecommunication Research and Innovation, Faculty of Electronic and Computer Engineering from Universiti Teknikal Malaysia Melaka. And this talk is actually in collaboration with IEEE ComSoc, which is Communication Society. So without wasting our time, I will start by explaining the wide range application of microwave technology as an introduction. So these are just a few examples of the diverse application of microwave technology. The versatility and unique properties of microwave itself make them valuable across numerous industry and discipline. So let's go through by one. First and foremost, microwave play a crucial role in the field of telecommunication for wireless communication, including mobile phone network, satellite communication, and also microwave link for data communication. So also they provide high speed and reliable wireless connectivity. So another significant application that maybe everyone knows about microwave is in radar systems, which utilize microwave for detecting and tracking objects in various industries and sectors as well. And microwave are also extensively used in, of course, in food processing, right? When we are using microwave as a cooking, heating, and thawing. Okay, and also for industrial scale, commercial food processing facilities is actually a microwave system for their efficiency and also try to make a uniform heating properties so that their food processing become faster and more consistent. Next, when we talk about the material processing such as drying, curing, sintering, and sterilization, they offer advantage of rapid heating, energy efficiency, and prices over controlled temperature profiles. Okay, and also in terms of environmental monitoring, microwave also take into advantage of using remote sensing technology to monitor environmental parameters such as soil moisture, ocean salinity, and also valuable data for climate study, disaster monitoring, for example. Okay, and about the microwave are also utilized in material characterization technique. This is right now commonly used and also practiced by recent research. They also dig into this application instead of material characterization of spectroscopy and impedance microscopy. They also use that actually for measuring the dielectric properties of the human tissue, for example, and other materials. And last but not least is about the generation of plasma. They use microwave also for manufacturing semiconductor surface treatment and other research area. So this is actually, there's many more microwave technology extent, but for now, for this topic, I will far beyond the biomedical field. So we will go into the potential for further innovation and advancement in microwave technology, promising in biomedical application. So in this presentation, I will delve into the breakthrough achieved so far and explore the exciting future prospect in microwave technology for biomedical application. So basically from cancer treatment to medical imaging, diagnostic, microwave offer a wide range of possibility for revolutionizing healthcare practice. Right, so let's go to the this is only several microwave biomedical application such as a tumor ablation. We can go through this application. This is also one of the primary application for biomedical using microwave. So for this application, they use microwave is to destroy tumor by giving the temperature. Okay, so this normally they will insert like a probe into the tissue or into the tumor, and they will targeting to destroy the tumor cells. So this will be like localized. They will be very focused on the tumor, which is not affecting the healthy tissue. And then this is the new method of ablation by using the alternating electric field with water molecule to generate heat energy through the water vibration and also the rotation. Next, we will go to hypothermia therapy. So hypothermia therapy is actually using microwave to raise the temperature of tumor. Okay, so this technology is to help, okay, to help and enhance the effectiveness of chemotherapy. Okay, so recent study has been done using the imaging technique to get better resolution of the tumor and also surrounding tissue, which is health tissue. So some of the study also integrate with other treatment. For example, they do the CT scan, and also the same time they will use the hypothermia therapy. And one of the other recent research study has been done is actually to improve the antenna design. They use array, and also they use improvise the lens in order to enhance the heating pattern and better in terms of temperature control. Alright, so microwave are used in medical imaging technique as well, such as microwave imaging to visualize and detect abnormalities in biomedical tissue. So the purpose is to provide non-invasive and real-time imaging for early detection, diagnosis, and monitoring various conditions, including the breast cancer. So imaging is nowadays I can see is more focused on the breast cancer. So this is actually the technology or the product that has been done by Professor Paul Amini and their colleagues. So they actually design like 16 antenna arrays, and they will do the transmitting and receiving the signal and collecting all the data to produce a 3D presentation of the breast. So this you can see that they will be the high resolution in terms of microwave imaging. So next we'll go to drug delivery system. So this is actually to enhance the release of therapeutic agent from targeted delivery vehicles or implant. So the purpose is to just to improve the control and localized release of drug, enabling more effective treatment while minimizing systematic side effect. So let's go to the diagnostic and monitoring. So this is also a part of it's not some, like many researchers is focused on this diagnostic and monitoring, because this is very important for us to monitor, to diagnose what is the impact of having, like, early detection. So the purpose is to provide accurate and continuous monitoring of specific health marker. So this is actually the example of using microwave split ring resonator sensor to sense the disease, which is limb edema, intracranial pressure, and also try to to monitor the level of skin burn Okay, so let's say the person have skin burn and then they were recovering. So we can use this type of sensor to monitor the skin burn healing level from level 1 and level 3 until the skin healed. So this is also one of the example of using the antenna of microwave in order to diagnose and monitor the disease. Now we go to fat intra-body communication. So intra-body communication refer to the communication between two devices or multi-devices or sensors, for example. So we have multiple devices that are now available in the market, but we need to have one channel which is very efficient and reliable channel to communicate those sensors. So this is actually related to FAT IBC, fat intrabody communication. So what is actually fat intrabody communication? So let's see this next coming slide. So this is actually my thesis, which is a new paradigm for intrabody communication. So what is intrabody communication? Intrabody communication is a short-range communication between devices, uses human body as a signal transmission, and currently we have multiple techniques such as galvanic, capacitive, and RF link. And also we have so many transceiver location, for example, surface to surface, implant to surface, and also implant to implant communication. So these are four categories that you might think that are not related, but they are actually have something in common between them. So let's have a look. What are they? So first, we took a look on the statistic. More than 1/3 of adults were obese worldwide. So studies have shown that overweight and obesity are major risk factors for a number of chronic diseases including diabetes, cardiovascular diseases, and cancer. So how about the elderly people? There are one syndrome called multiple organ dysfunction syndrome, which are caused by aging. The common sequence of a failure in organ is heart, lung, kidney, and liver. So you can see there are multiple organ dysfunction in this. Next is a non-communicable diseases. This is actually the disease that cannot pass from person to person. So NCDs are actually the biggest global killer today and responsible for almost 70% of all death worldwide. So NCD are also including multiple chronic diseases such heart, stroke, cancer, diabetes, and lung diseases. And now we go to the last category. So technology continues to get closer and closer to our bodies, right? So from the phone in our pocket to our smartwatch in our wrist. But now, for some people, it's getting under their skin. So in Sweden, thousands have had microchip inserted in their hands actually. So the chip are designed to speed up user daily routine and make their life more convenient. So this is actually the example of microchip that has been implanted under the skin. So you can see this is also one guy. They try to open their apartment, okay, by using this chip. So what are the common between these all? Of course, they need multiple implanted devices due to multiple chronic diseases, right? And then last, they need to continuous health monitoring. So meaning that we need some kind of reliable communication channel in order to support multiple implanted devices and continuous health monitoring. So what I'm proposing is the conceptual rendering of intra-body communication through the fat tissue. So since we need to have reliable, efficient, secure communication medium, so this is what I'm proposing by using fat tissue. So maybe you will think about why fat tissue, right? So this will be the study about behind the technique that has been used. So from this result, you can see that muscle tissue has 3 times more attenuation compared to the fat. So for example, at 2 GHz, fat channel is about minus 30 dB, while muscle channel has about minus 94 decibel. So this is proof that the fat is feasible as a communication channel. So in order to study and demonstrate in the laboratory environment, we design and develop the probe prototype, which acting as a transmitter and receiver. So this probe launched the microwave signal through the fat tissue. So here there are 3 types of prototypes. Okay, first is focus at 2 GHz. So this is actually we developed by ourselves by fill the rubber to mimicking the fat tissue, and also we wrap with a copper tape. So the second prototype, we improve our probe development by designing a new R band, which is support from 1.7 GHz until 2.6 GHz. And this is actually focused at 2.4 GHz ISM band. And this for this probe, we also fill with the rubber, but we fill with vulcanized rubber, which is quite hard. And the third prototype, we try to shrink the size of the probe, and we actually design at F band from 4.9 GHz until 7.05 GHz. For this probe, we focus at 5.8 GHz ISM band. So the development of the probe as well will be the same actually as a second prototype. It's only the antenna type which is inserted in the prototype will be different. Okay, so in order to do some measurement to mimic the real human tissue, so we use this material and tissue for the experimentation. For phantom, we use a agar-based phantom. For fat, we have a multiple type of phantom, which is adhesive putty, synthetic rubber, vulcanized rubber, and oil-based phantom. So the reason why we have so many type of fat phantom is actually to compare which one is the closest to the human tissue type. And for the muscle, we use the agar-based phantom. And when we do some experimentation and characterization of the channel by using ex vivo, we use the 3 layers skin, fat, muscle by having the porcine belly tissue. So this is the dielectric properties of different material of the fat tissue, and you also can see this compared to the human tissue by from the Gabriel from the database. Next, we do the characterization of the fat channel. So first, we do the characterization at 2.4 GHz, and this is the simplification structure of a human model. So we know that the human anatomy will be quite difficult, and then we try to simplify it so that we can have the 3-layer structure. So for this characterization, we divided into 3 cases. Okay, case 1 is a 3-layer waveguide section, which comprises of skin, fat, and muscle. So at the end of the channel, we will put probe 1 and probe 2 as a transmitter and receiver. Case 2, we try to get an ideal cases which have not the ideal cases. We have like only the dielectric rectangular waveguide without the skin and muscle. So we just want to know what happened if there is no skin and muscle. And case 3 is about parallel plate waveguide. So for this parallel plate waveguide, we try to study what happened to the channel without any leakage, because we know that if we put copper plate on top and the bottom of the channel, there will no leakage from the channel. So from this figure, we can see the path loss of 3-layer waveguide section is between the fat dielectric waveguide and parallel waveguide. It has shown that the parallel plate waveguide is an ideal case without any leakage, and the signal is leaked out without the presence of the skin and the muscle layer. So we prove that if we have no skin and muscle, so we will have leakage on our communication. So by having the human structure, which is consists of skin and muscle sandwiched together, so we can confirm that the fat tissue layer will be better for communication. So this is the electric field at 2.4. So the first figure is on the free space channel. So we can see this probe is actually has been optimized to propagate in the fat tissue, meaning that if we try to transmit the microwave through the free space, so we won't get any result on the other hand, which is on the receiver part. So when we have the second figure, which is the fat layer channel, which this is actually is not ideal cases because there is no skin and there is no muscle. So this is only the fat tissue, and we will have the transmitter and receiver on the other hand. So you can see here is the blue electric field. So this is electric field is leaked out from the channel. Okay, and the 3-layer fat channel, which is a skin, fat, muscle, you can see the electric field is actually confined through the fat tissue. Next, we will characterize the fat channel at 5.8 by using our small probe. So the reason why we designed the small probe is actually to study in terms of polarization, and also try to transmit as an implant to implant communication. So here we divided into type A, B, C, and D. So here is the configuration of each type. So this is actually to study what happens if we have extend the width, which is in the human tissue, and when we have an extra thickness on the fat, and also we have like mimicking the implant to implant communication in type D. So this is the measurement setup. This is a phantom measurement setup, which is the skin, fat, muscle, and then this is the ex vivo experiment setup. So here we can see the probe has been placed on each side, and then we will rotate the probes to see what happened to this channel when we have misalignment or something like that. So we study on that characterization. Okay, so this is the result of characterization for each type. So type A, type B, type C, and type D. So this is the comparison. And this is the summary of path loss at 2 GHz, 2.4 GHz, and 5.8 GHz. And you can see for phantom, it's 1 decibel per centimeter for phantom, while the path loss for ex vivo is 2 decibel per centimeter. And for at 2.4 gigahertz, we have very good path loss, which is 0.7 decibel per centimeter for phantom and 1.9 decibel per centimeter path loss from ex vivo. And for 5.8 phantom, we can see is actually 6 decibel path loss per centimeter. This is very high, almost double from the path loss for ex vivo. This is actually due to this due to the phantom that we have used during the experimentation. So this is the phantom for oil-based phantom, which is having slightly higher in terms of loss tangent. So that's why you can see this path loss for phantom is higher. So in order to establish the transmission channel, so we need to have 5 requirements. First, we talk about the distance. So for fat intrabody communication, the distance will depend on the fat tissue in human body. So also the distance between each organ, for example, lung to liver. So the maximum or the average distance is about 10 to 15, or maximum is 20 centimeter distance. So when we talk about the fat intrabody communication, so we will talk about the distance is actually throughout our body. Next is about performance. So since we use fat tissue as a communication channel, so we know that the fat tissue has lower loss compared than the other tissue. So meaning that it can perform better than the rest of the other tissue, for example, muscle. This is due to the dielectric properties of the tissue, which is only around 5, and the other tissue, for example, muscle, skin, is very high, which is about 30 to 40 permittivity. So that is actually contribute to the losses as well. Then the capacity. When we talk about the capacity, since we are using the microwave frequency, and we can actually support high bandwidth, so therefore we need to also take into consideration the frequency operating, and also the frequency that has been used, and also the absorption from the tissue itself. So we need to take into consideration while choosing what is the frequency that can be used. And then when we talk about security, we know that the human anatomy has 3-layer structure, which is skin, fat, and muscle. So the confinement of the skin and muscle is actually reduce the leakage in the transmission. So whenever we have fat, so on top of the fat, we will have a very high permittivity, which is skin or muscle, and on the bottom of the fat tissue also we have very high permittivity, such as a muscle. So the confinement of the high permittivity is actually helps the transmission go through along the fat tissue. And lastly, when we talk about consumer, of course, since the fat tissue is omnipresent in the human body, so we can actually place multi-sensor node inside to meet the user's demand, especially for those are having the multiple chronic diseases, what I've been explained in previous slide. Okay, so next we go to this presentation, which contain images that may be disturbing to some audience. So this is actually the cross-section anatomy. From Okay, so from this image, we can clearly see that the fat are omnipresent in nature and it covers the important organ. So now I will close up one of the images here. So this technique that we propose here is using fat as communication channel. So let's say we have two sensor nodes implanted in the fat tissue. This signal will use fat as communication channel. So by this technique, the sensor node will choose the path to reach the organ by having another nodes in the body. For example, if we are placing these other three nodes, so the sensor will choose which um, is the best path to go when we want to transmit from node 1 to node 3 or from to reach important organ. So that is actually the fat intrabody communication. So that is not biomedical application, but whenever to support the multiple biomedical devices, we need to have reliable and efficient transmission channel. Now let's move to challenge and limitation for biomedical application by using microwave. So when consider biomedical application using the microwave frequency range, there are several challenges and limitation, or maybe we can say criteria that are very important. So here are some criteria to consider. This is a microwave frequency. So normally range about few hundred megahertz to like 10 gigahertz from microwave. So the selection, the frequency selection should be based on specific application or maybe desired outcome. So, but we need to also take into account the tissue penetration depth, absorption characteristic of targeted tissue. For example, if we want to have, if we want to implant our antenna or our sensors inside the muscle tissue, we need to know what are the penetration depth for that tissues and also what are the absorption rate for that particular tissue. So this is actually very important, and also we need to consider as well the potential interference with other devices. For example, interfere with the pacemaker. So we need to avoid that in order before we do some antenna designing or something like that. So frequency selection is the one criteria. Then when we talk about absorption and penetration, when we want to implant inside the tissue, different tissue has different absorption and penetration characteristic, right? So we need to ensure what are the frequency has been will be used or chosen in order to optimize absorption in the target tissue. So this is actually also we need to minimize the absorption surrounding the healthy tissue. Next, heating and thermal effect. Microwave energy can induce heating in tissue. So when if we want to do some designing, we need also to select the frequency range that ensure control and localized heating without damage any health tissue. So the heating rate should be very careful monitored and controlled to prevent the thermal damage. Next, we go to safety. So safety is the most important in biomedical application. So the selected microwave frequency also should follow the established safety guideline and standard. For example, if you want to design implant antenna, So we need to also follow the guideline of ISM, for example, implantable frequency standard, for example. Okay, and then we also need to know what are the exposure limit for certain application. So these are the standard in Malaysia. So this is the RF, EMF standard in Malaysia. We need to follow MCMC, ICNIRP. So they also have standard in ITUT and also IEEE. This is like a standard that has been used widely. So just make sure that the exposure limit, for example, should not exceed the limit, so that it won't affect the human tissue. Next is the regulation consideration. Any biomedical application using microwave should comply regulatory guideline and obtain necessary approval before doing anything, right? So in Malaysia, we need to follow MDA, which is Medical Device Authority, and we also have MMC, and the other one is the FDA. So this is the maybe different country will have different regulation to be considered, and otherwise you just need to have follow this regulatory consideration. When we talk about antenna, so the chosen microwave frequency range should also demonstrate the efficiency in achieve desired outcome to specific application. So for example, you already designed some sensors, so you need to have you need to follow the preclinical and clinical studies to evaluate how effective your sensor and how safe your sensor. So that is actually is very important for actually to if we want to go for diagnostic application or therapeutic application. So this is must be must be verified before do anything. And then compatibility and integration. So when we want to introduce or we want to design something, so we need to ensure that our device can integrate well with existing medical technology or maybe procedure. For example, you already have one device that you want to want to monitor. For example, if we want to monitor the bone healing or skull healing, so you need to follow what are the procedure has been done clinical in the hospital. So you need to consult medical practitioner before you do some designing. So maybe you need to know what are the best position or what are the best physical structure for your antenna or for your device before you do some testing in the hospital. Or maybe if you already have something or they already have some existing machine that you want to integrate, so you need to know what are the power has been used, or you need to know like to facilitate integration into clinical practice. And then practicality and cost. So practical consideration, of course, you need to consider what are the costs of the equipment. So you need to know, you also need to design which is very friendly user, easy to use and easy to access anywhere. So it will be good if you can have wirelessly remote or something like that. So you need to expand your application in terms of microwave to be practical and low cost. Okay, so the balance efficiency with practicality and cost effective we need to be balanced so that your product is well you can uh, commercialize is very easy. So overall, this is like challenges and limitation. So I would say like a criteria perhaps in order to do something. So by using microwave frequency, so you need to highlight those point beforehand. Okay, so we already talked about the biomedical application. So currently, there are many researchers already focused on the microwave technology. What are the microwave technology can be done or can be used for biomedical application, right? So for future prospect, there are so many exciting possibilities. So let's have a look. These are some potential future prospect for microwave biomedical application. So we can go to point 1, advancement in microwave technology for enhanced precision. So microwave is likely to continue advancing in the field of cancer treatment. So future development maybe can improve the treatment probe and also can combine therapies and integrate microwave ablation with other modalities. For example, drug delivery, so you can integrate two treatment, and then this advancement also aim to enhance treatment efficiency, minimize side effect, and also you can do like precise cancer therapies. So this will be the future prospect that you can be improved. And then the second is integration of microwave with other biomedical technology. Okay, and then we also have a real-time monitoring and feedback. So in terms of advancement in microwave technology could enable real-time monitoring and feedback during the procedures. For example, we want to improve the sensing and imaging capabilities. So this actually can allow healthcare professional to monitor the temperature, tissue response, treatment efficiency in real time. So this feedback is actually can guide treatment adjustment to optimize therapeutic outcome. Oh, sorry. And then point number 4 is point of care diagnostic. So microwave have potential to revolutionize actually point of care diagnostic. So we tried to design miniaturized microwave device and sensor. We can develop that for accurate detection for specific biomarker or cancer, for example. So this could enable faster diagnostic. So the patient can bring back home the device and then they can test everything. Then we can actually remotely monitor. So this actually can help to early disease detection and also improve management diseases or chronic condition. So this is actually one important point for me. So for example, we stay at a rural area, so it's very hard to get facilities or transport to go to the hospital. Then it would be very good to have some portable devices for those who are needed. Then they can monitor their health, everything from home or from remotely. Sorry. Okay. And then wearable and implantable devices. The miniaturization and integration of microwave technology can lead to the development of wearable and implantable devices for biomedical application. So this device can continuously monitored health parameter. So they also can localize therapy, provide real time. So this is actually one of the future prospect that can look into. And point number 6 is theranostic, which is the integration of therapy and diagnostic. So this hold great potential in microwave biomedical application. So we combine microwave-based imaging and therapy platform, then we can provide real-time monitoring of treatment response. So this is also allow personalized treatment. Then we can also approach effective therapy, reduce treatment duration, and also enhance the patient outcome. So by having the combination of both therapy. And lastly is artificial intelligence integration. So we know nowadays like AI is everywhere. Integration microwave technology with AI algorithm could revolutionize biomedical application. So AI can aid in optimizing treatment planning, predict like do the prediction on treatment response, and they also can analyze complex data. So this is actually a boom to improve diagnostic accuracy. So this is very good actually to look into for future prospect. Okay, so as a conclusion, microwave have emerged as a powerful tool in biomedical application. So there are very huge potential to transform the landscape of healthcare. So by harnessing the unique properties of microwave, we can pave the way for more precise, minimal invasive, improved diagnostic and enhanced patient care. So the future of microwave biomedical application is indeed bright and holds immense promise for the advancement of healthcare practices. So thank you.